Hello and welcome to our next lesson on vectors, where today we are now looking at algebraic vectors. And we're going to start with our r squared and finish off with looking at r cubed, but it is a very similar process for all the things that we're looking at. So our learning goal today is to represent and operate vectors algebraically in two and three-dimensional space and also interpret their geometric meaning. And just to give you a reminder of our definitions, when we were looking at vector operations in our last lesson, we were mostly looking at geometric vectors. And remember, those are location independent, so we just care about the magnitude and direction. But now we're looking at algebraic vectors, which are given to us with the coordinate system. So starting with our r squared, we are just going to have x and y. And then as we move on to r cubed, we are going to add that z component in as well. So we do have in r squared two special vectors, which are the unit vectors. So the unit vectors are just 1, 0 and 0, 1. And they are defined as I and j. So I is the x component and j is the y component. And these have a magnitude of 1. So if you look on our coordinate system here, and again, not drawn to scale, but this is 1 and this is 1, and they go in the positive x and y axes. So they are going to be very useful for us in just showing a different representation of vectors in R squared, but they're also our standard basis vectors. So they're very important for vector notation in both r squared and r cubed, and later we're going to see how they will be different in r cubed. So vectors, any vector OP can be written in terms of the unit vectors. For example, if OP is OA plus OB, then we can write this as A times the unit vector I, plus B times the unit vector J. So this is point P, which has an X component of A and Y component of B. And these are right now scalars. But if we draw this vector here that has the direction given by this point, then we can also write it alternatively as AI, which is the X component A times the unit vector I, and then the Y component B times the unit vector J here. So for any random A and B, and here it does appear that A is 3 and B is 2, so we can work with that. But we're asked to identify and draw the vectors AI and BJ. And again, you don't necessarily need to know that whether the values are 3 and 2, especially because here we can kind of see it's maybe a little past 3, so maybe not exactly 3. But the point here is when you're drawing this, you start at the origin and you go to the line from which the point P is perpendicular to the x-axis, and this is now AI. And remember, I is our vector, so only I gets the arrow. And similarly here, for the y component, we draw a perpendicular line from the point to the y-axis. And if I extend from my origin to now this point, it does have to be like on the y-axis. Okay, approximately like that. Then this is now bj, which is a scalar multiple of the unit vector j. And what is it being multiplied by? B, which we got from the point there. So, for example, if you're given the vector OP and its coordinates are 3, -8, then you can just write this as a sum. 3 times I minus 8 times j. So this -8 is from here, the 3 is from the x component, and we just have our unit vectors. Now here, we're given a series of vectors, and we're asked to write them using the unit vectors. So remember, this is point O, our origin. So all of these vectors are starting at point O and going to different points on this coordinate grid. So starting with OP. So OP its x component is 3, which means my I unit vector is being multiplied by 3, and my j vector is being multiplied by 4. So this is 3I plus 4j. For OR, we have -4 times the unit vector I. But we see that the j, for j, the b component is 0. So really, this is plus 0j, which is, because this is scalar multiple, this would give you the 0 vector, and we don't need to write the 0 vector. So this is just -4I. Now, OT, we have 4I minus 2j. And again, I'm just using those components. OQ, we go up there, we have -2I plus 3 times vector j. And now OS, this is now also a special case where our x component is 0. So really we have 0 times I minus 3j, but this is the 0 vector. So this is 0, and remember this is also the 0 vector, and we don't need to write that. So then this is just -3 times the j unit vector. Now, if we are given two vectors, OP, that is given by the coordinates AB, and the vector OQ, which is given by the coordinates CD in R squared, we want to find the resultant. So OP, remember, is defined as A times I plus B times J. So now following that, OQ is defined as C times I plus D times J. And A, B, C, D are scalars in the set of real numbers. So then, using these two definitions, this part's not really necessary, but I'm just trying to show you because this is OP and this is OQ, just in their unit vector representation. Then really, this is now where I'm using properties of vector addition from last class. So I can take these two scalars and add them, A plus C times I, and then B plus D in brackets times the unit vector J. But then this in itself is a vector representation with the unit vectors, and its x component is A plus C, and its y component is B plus D. So this is in fact showing us a new way to add vectors in algebraic with algebraic vectors. It's actually a lot easier than what we've seen so far. We don't have to use any sine cosine law here. We're just using the components. And so to generalize that now, vector addition in R squared with component form is pretty much you add the x components and the y components. So given OP, which is determined by the point P and its components A, B, and then Q has its components C, D. Then when you add them, and this is just that parallelogram formation, this resultant vector, and this is OR, this is then given by A plus C and then B plus D. And really what you're doing here, if I draw this perpendicular line, this is A. And if I take this, maybe let me change this one. And if I go down here, this whole part is C. So really, when I take this OQ vector and I draw it from here, this part here, if I go down, now I can say that only just this part is C. And remember, this part is A. So then, at the point where I'm getting to point R, so if I draw that parallel line there, this is A plus C. And the same thing you can do with the y-axis to show that it is B plus D. Now, scalar multiplication I'm going to show you as well because, again, it's really easy and it follows similar to what we just saw. And then we're going to do some examples with it. But when you have vectors in algebraic vectors in R squared, then you are multiplying it by a scalar, and in this case, our scalar is m, then both the x and y components are multiplied by the scalar. So for example, if you have U is 3, 4, and you multiply this 3U, then this is now 9, 12. I just multiplied the x by 3 and the y by 3 to get 12. Now, if m is greater than 0, you are moving in the same direction. Your direction doesn't change. You just have that the magnitude of your vector is changing, and it follows the same pattern as last time. If m is between 0 and 1, you're shortening it. If m is greater than 1, you're lengthening it. And if m is equal to 1, you have the same vector. Now, if m is less than 0, then when you multiply it, you actually have the opposite vector. And again, the same thing will hold. If the magnitude of m is between 0 and 1, you're shortening the vector in the opposite direction. If the magnitude of m is greater than 1, you are lengthening the vector in the opposite direction. And if m is just equal to -1, then you have the same vector, but just in the opposite direction. So it's the opposite vector. So let's start here. We have the two vectors OA, or just A, given by its components 1, 3, and the vector OB, or B, given by 4, -2. And we're asked to sketch both vectors on the graph. So let's start with sketching both of those. So just looking at my numbers, maybe I can work with 1, 2, 3, 4, and here -1, -2, and here we have 0. And same thing, we go up 1, 2, 3, 4, and -1, -2, -4. So first what I'm going to do is just label those points. So A is 1, 3. So keep in mind, this is just the point A. We don't have the vector just yet. And then B is 4, -2. And now I can draw the vectors starting at the origin. Remember, that's point O, so this is OB, or just vector B. And now same thing with A. We have OA, and, or just simply A. Now we're asked to determine A plus B and A minus B and sketch the resultant vectors on the graph. So A plus B now is just going to be the x components added together, so 5, and then 3 minus 2 is just 1. Now, A minus B, this is just A plus -B, right? So, and maybe I'll just write it for you here. -B, this is just our scalar multiple. It's going to be -4, 2. So I'm adding now this to A. So then we have -3, and then 3 plus 2 is 5. So now let's draw these, and let me call this point C, and this is point D. And B, I'm going to use, let's do red for both of these. So this is C and D. Okay, so C is going to be 5, 1, and D is going to be -3, and then 5. This is 5, 1. And now this I can draw here is going to be A plus B. Oh, my bad. See, I got a little confused when I drew it, and I was like, wait, this isn't adding up because I made a mistake here. This is -4. I have to redraw this. It's 4, -2, so it should be there. 2. Okay. And now that actually makes more sense because because I saw that my x component is greater, and I was like, that's not possible if we're going in the other direction. But now that actually makes sense because we have the 1 and the 4, so it ends up at 5. And here we have 3 and -2, and their sum will just be 1. And now here we have -3 and 5. And now this actually works out. And this would have been this actually works out too because we are going now in the opposite direction for B. So it would have been somewhere like here if we go opposite direction for B. And then that makes sense for our difference of A minus B. And then let me just label this. This would be A minus B. Okay, there we go. So now, sometimes you're not given the vectors. You are just given 2 points. So for example, A is given by x1, y1, and B is given by x2, y2. And you want to find the vector A, B. This is a bit harder because we're not starting at the origin. But really, what we're going to do and how you're thinking of it is you're drawing the position vector OA and the position vector OB, and then you're finding that resultant vector. And this, if you now started from the origin, which will be OP, this will be equal to here. And what you're really doing is finding the difference between the x components and the y components. And the magnitude is just going to be x squared, or the x component squared and the y component squared, which were these two values here. Now, this might have been a little familiar to you, and it should be because it's really the formula for the distance between 2 points, which you have seen in math before. And really, it's obtained from the Pythagorean theorem, because if you form this, we have a right triangle, and then we're just finding the hypotenuse here. And so let's see it as an example now. We're given 3 points, A, B, and C, that form a triangle. And if you're a visual learner, I really suggest you try to graph these 3 points and connect them and see the triangle that's formed for yourself. But with our triangle, what we really want are the magnitude of the 3 sides because we're asked to find the perimeter of the triangle. So we want the magnitude AB plus the magnitude BC plus the magnitude CA. And that's really just if you have, and this is not the same necessarily triangle shape, but A, B, C, then we want AB plus BC plus CA. And because it's magnitude, it doesn't necessarily matter if you do AC or CA, but I just wrote them in that direction so you know that we're going from A to B, from B to C, and from C to A. So starting with AB, I will find the difference of the x and the y components. So I did 4 minus 2, and then 7, take away -5, and I will end up with 2 and 12. And so the magnitude here is, again, from Pythagorean theorem, this is 2 squared plus 12 squared, and the square root gives me square root of 148, which is approximately 12.2. And 1 or 2 decimal places is really okay for these lessons when you're finding exact value or approximate value. Now, same thing for BC, I get 0.4 -6, and its magnitude is approximately 7.2. And finally, for the side length CA, I get -6 and -6, and its side length is going to be approximately 8.5. And because we're working with just coordinates, we don't have necessarily units here, so that's why we use a generic unit. So all of these have a generic unit, which could be, if in a context you're saying 1 on the scale is 1 meter, then these would be meters or centimeters or so, whatever you're working with. So then the perimeter is going to be 12.2 plus 7.2 plus 8.5, which is 27.8 units. Now keep in mind, this is a scalar quantity. It just has units. We don't work with direction because remember, magnitude is a scalar and the vector itself, which has a direction, will be our vector, but the magnitudes are just scalar. So we just need units there, no direction, and our work is done. And again, if this is not clicking right away, I really suggest plotting these points, draw the lines that connect them to see the triangle form, and then try to use Pythagorean theorem yourself or the formula for the distance between 2 points to be able to make connections to what we just did here. Now, we're given three vectors here, given by their component form. So vector A is 5, -6, vector B is -7, 3, and vector C is 2, 8. And we're asked to calculate the magnitude of A minus 3B minus half of C. So really, what we have to do first is find what this expression here is as just one vector. So A minus 3B minus half of C. So I'm starting with A, and now minus 3 times B, which was -7, 3, and then half of C, which is 2, 8. Now, if I distribute these are just scalars, then I have A is just itself. This becomes 21. I distributed also the -3 here, so it becomes 21, -9. And here I've also distributed the negative and half, so it's -1, -4. And now I just added the x component. So 5 plus 21 minus 1 is 25, and -6 minus 9 minus 4 is -19. So this is the resulting vector. Now, taking the magnitude, this is just 25 squared plus -19 squared, and take its square root, which is square root of 986, and it's approximately 31.4. And that will be it. Now, let's expand to our cube. So again, it's very similar, but now we have that third component, which is for our z-axis. So a vector OP is given by ABC in our cubed. And now we have K here, which is our third unit vector in the R cubed space. Now, one difference also is because these have tuples of 3, when we define our unit vectors I and j, it does follow that I is the unit vector for the x-axis, j is for the y, and k is for the z. But now you have to add that third 0 in there, and same with here. So 1, 0, 0, here it's 0, 1, 0, and k, which is the the z component, is going to be 0, 0, 1. And these are unit vectors along the positive x, y, and z axes. And again, similar to in R squared, every vector in R cubed can be represented uniquely as a combination of I, j, and k. Because again, if you have one component given, so if you have 2, 3, -5, then this is the same position vector starting from the origin because of its components. You can't change those. Any vector you draw will be that same vector. It will be coincident with that vector, so it is unique. So let's see a few simple examples just to help you make connections. So starting with vector OP, which is given by 2, 1, and 5. So the 2 tells me that I have to multiply the unit vector of I by 2, so 2i. This one is the same as j, so just plus j. And then I have a 5 in my z component, so this is 5 times the unit vector k. Now, if you have a negative in there, this will just be -6i. Now here, because my y component is 0, I can just exclude j. I don't have to write 0j because remember, again, 0j, 0 times j, this is a scalar. This will give me the 0 vector, and the 0 vector doesn't make a difference. So we can exclude it. So we just have -6i plus 7k, which comes from the z component. And now we can also have this, because A, B, and C are any real number, we can have any value here. Generally, I'm showing you a lot of friendly numbers, but you can have square roots, you can have pi, you can have rational numbers, any possible value of A, B, C, and it will still follow the same rule. So here, we're actually given now the vector using unit vectors, and we're asked to write it in component form. So this is just 1. -4j is going to give me a y component of -4, and 2/3 of k is going to give me 2/3 third for the z component. And that would be another representation of my vector. And in all of these are the same. These two vectors are just two different representations of the same vector. So either using component form or using the unit vector, or in this case, we can also say the standard basis for r cubed. Now, vector addition in R cubed with component form, again, follows the same pattern, but now we just have that Z component in there. So given OA, which is ABC, and then OD, which is DEF, then the resultant, which is vector OA plus vector OD, we just add the X components, which is A plus D, the Y components, which is B plus E, and the Z components, which is C plus F. Now, here I'm also showing you with that unit vector notation. If you have A times I plus BJ plus CK, and then for OD we have DI plus EJ plus FK, this is just properties of vector additions where we can have the scalar components added, or the scalar coefficients added together, so A plus D, B plus E, and then C plus F. And then this is a unit vector representation which matches with this component form. So these two are the same. And now here I just shown you a little bit visually just so you see it, but if we have OA, which is ABC, and then we have OD, which is DEF, then the resultant will be A plus D, B plus E, and then C plus F. And it is a little bit harder to visualize in 3D space, but that's why algebraic vectors are really helpful because we don't necessarily have to be drawing those vectors. We just work with their components and just add them together. Now, same with scalar multiplication. If you have a scalar m times a vector OP, and OP, again, from above is given by ABC, then really you're just multiplying each of the components by m. So MA, MB, MC, or in the unit vector notation, we have m times A times the vector I, and then MB times the vector J, and MC times the vector K. And these just come from here, MA, MB, MC. Now, the magnitude of a vector in R cubed is, again, same process, but now we have to include that C component as well. So it's A squared plus B squared plus C squared, and we take the square root there. Finally, our last concept from R squared was the position vectors and magnitudes in R cubed. So if you're given two points, A and B, with components x1, y1, z1, and B is x2, y2, z2, and again, these are points, not vectors, but the resulting vector from A to B can be given by the difference of their components. So x2 minus x1, y2 minus y1, z2 minus z1. And if we let this be equal to ABC, this is now the resulting position vector OP. And its magnitude is given by A squared plus B squared plus C squared and the square root of that, or because A is just x2 minus x1, is really these values squared. And again, just to show you visually, we have A and we have B. So this resultant vector here, so this is really AB. Then this is now OP, but the only difference is this starts at the origin, whereas this goes from A to B. But they have the same magnitude and they have the same direction, so they are equal vectors, but just with different starting points. So let's see what that would look like with some numbers in. So A is given to us, the point A is 6, -8, 15, and B is -2, 4, and 9. So they're 2 points in R cubes, and we want to find OA, the position vector from origin to A, the position vector from origin to B, so OB, and then we want to find the vector AB and its magnitude. Oh, and keep in mind, these two are also magnitudes because of the two lines there. So OA, and really when you're doing OA, you have 2 points as well, but your point O is 0, 0, 0. So when you do that difference, you're doing 6 minus 0, -8 minus 0, 15 minus 0, which is just going to give you as OA, it's going to be same, 6, -8, 15. And then when you find the magnitude, it's 6 squared plus -8 squared plus 15 squared. And this is taking the square root of that. It's square root of 325, approximately 18.03. Now, same thing with OB. We're now using -2 squared plus 4 squared plus 9 squared. And we get square root of 101, which is approximately 10.05. Now, AB, oh, and I'm missing my vector sign here, because this is now a vector, it's not just a line, is we start with B, -2 minus 6, 4 minus -8, and 9 minus 15, which gives us -8, 12, and -6. And now the magnitude here will be just from this value here, -8 squared plus 12 squared plus -6 squared, and the square root of 244 is approximately 15.62. Now, I am going to show you one more thing here, and it's if we do BA, which is, you start with 6 minus -2, and then -8 minus 4, and 15 minus 9. And this will give us 8, -12, and 6. And you can see that this, and this is what we had seen in our very first lesson, is negative AB, right? We see here we had -8, here we have 8, 12, now we have -12, and -6 is 6. Now, if I take the magnitude of BA, this is going to be square root of 8 squared plus -12 squared plus 6 squared. But because we're squaring them, then these two are the same, these two are the same, and these two are the same. So ultimately, this also ends up at 244, square root of 244, which is approximately 15.62. So this goes to show you again that we have opposite vectors. The magnitudes are going to be the same, but just their direction is opposite direction. So this one is going to be the negative of the other. And that was it for our algebraic vectors. So as you can see, they're a lot more helpful and easier to work with than our geometric vectors, but they're both useful nonetheless. And so get some practice for today as well. You do have a practice set on Google Classroom that you can complete, and some extra questions here for you. And as always, don't hesitate to reach out if you have any questions, and I will see you all next class.